Hey Physics 30s, it's Mr. Hofstad here with the ninth and final lesson of Unit 5, Quantum Mechanics, which can sound a little bit intimidating, I will admit, but what we are required to know for the sake of Physics 30 here isn't too overwhelming. We're just barely scratching the surface, just giving you a taste of what you could potentially study further in university. I unfortunately didn't get a full quantum mechanics course in my engineering program, but I did do a little bit of fun side reading, and I encourage you to do the same because this is, this hasn't really changed in the last 80 years. This model has held true better than most. It's not a perfect explanation of the world, or of atoms, however you want to look at it. It is better than Bohr's model or any of the previous ones, and it does a great job of explaining those problems that Bohr ran into. So let's dive right in. In the 1920s, we have de Broglie. He's kind of working off of Compton's stuff. Compton, if you look back in the notes, was our scientist who determined that we can have high frequency EMR with momentum, right? So this is where we have a wave acting like a particle, because right until then we've thought of electromagnetic radiation as only being a wave, but he did some experiments and created this new understanding of electromagnetic radiation being a particle, right? Both a particle and a wave, which is where this idea of wave-particle duality comes in. So Compton was the one who thought of light waves being able to act like particles because they had momentum, right? They start to behave like particles. Then a couple years later, de Broglie kind of thought about this in the opposite way. So, right, we have Compton thinking of light as a wave acting like a particle. Now we have de Broglie thinking about it the opposite way, right? Something that we know to be a particle, or we've always considered to be a particle, like an electron, for instance, which is what we're going to focus in on here. He thought that a particle might have some wave-like properties, just like a wave can have particle-like properties. So de Broglie suggested, right, he thought that the world was nice and symmetrical, which he wasn't too far off, right? That matter could show wave-like properties, just like a wave can show particle-like properties. Why can't it work the other way? And it turns out it actually can work the other way. So this is our ninth principle of physics, wave-particle duality. We've touched on it already. Now we're just looking at it in a new quantum mechanics light. So principle of physics 9, wave-particle duality. Right? It can either be thinking of wave acting like a particle, or what we're focusing on here, a particle like an electron acting like a wave. So Compton had come up with this idea of P, which is momentum, equaling the our constant here, H, which is Planck's constant, either in joules or electron volts, divided by the wavelength of that photon. And we're combining this with the momentum of a particle, mass times velocity, back to Unit 1. And when we combine these, right, we can see that we're able to determine wavelength based on mass and velocity. So something with mass will also have an equivalent wavelength, which is a little weird. But this will only work for things that are traveling much slower than the speed of light, right? Double thing means double, less than symbol means much less. Wow, my writing is just painful on this. Much slower than the speed of sound, or speed of light, sorry, C. So we've got our wavelength in meters, Planck's constant, more often, right? So in this case, since we're working with kilograms and meters per second, we needed to use joules, right, to keep all of our units compatible, right? We need to be joules per second since we're working with meters, kilograms, meters per second. Right, then we can find the equivalent wavelength of matter, the matter wave, when we know its mass and its velocity. All right, take a look at Mr. Holloway's video for this example. I'll jump right ahead to the evidence that really let this idea of particles acting like waves come to fruition. So just like we had a double slit experiment for our last unit with electromagnetic radiation, we had Young, right? Young's double slit experiment showing that light was actually acting like a wave when it traveled through these two slits because we had these interference bands, right? Constructive interference and destructive. So an obvious way to test de Broglie's theory, if particles can actually act with wave-like properties, was to replicate Young's double slit experiment, but instead of using light, using electrons, which are definitely a particle. So we're firing electrons through these slits, right? Putting a particle through a slit. What we expect is we expect to see two vertical lines, right? Just like shooting, I don't know, tennis balls through a doorway, right? Two doorways. They should just form a single line per slit across from it with no kind of dispersion out, right? They're just traveling straight, no interference. But that's not what they saw at all, right? To their surprise, the electrons formed many lines, just like Young's double slit. That means that the electrons were showing diffraction and interference, where we had constructive interference at these points where lots of electrons were hitting our screen, and destructive interference where there were almost none. So this shows that electrons have properties of both waves and particles. So we're able to now say that particles can act like waves and waves can act like particles, which is our 9th principle of physics, wave-particle duality. Okay, the quantum mechanical model of the atom. There's a lot of scientists who worked on this, but we're going to credit it to Schrödinger in 1926. Think about Schrödinger's cat, a famous quantum mechanics thought experiment. Watch a nice little TED Talk on that if you want to get on board with Schrödinger and his way of seeing the world. So this model is still currently being used. Right, there's been some changes to it, and it's slowly being replaced or trying to be replaced by string theory. But this is our best interpretation of atoms and how they interact with each other and themselves. And if you're taking any sort of chemistry courses in university, you should spend quite a bit of time on this model. Different SPDF orbitals, different shapes, and types of probability functions that will occur. So in order to fully understand the atom, our scientists had to embrace wave-particle duality of the electron. So as de Broglie kind of showed that even though electron we've thought of as a particle, right, can act like a wave, we now need to bring that into a new model of the electron, which is the quantum mechanical model. So we had growing evidence that the electron in orbit around the atom behaves more like a wave than a particle, right? This is a problem since a wave has no definitive position, right? They are always oscillating up and down, right? You can't just pinpoint it to one spot, right? It has this kind of continuous motion to it, right? And they're spread over a much larger area. So instead of having a single electron at one point, we now have it existing as a wave in multiple points, which creates some problems, but it is necessary to get this new improved model of the atom, the quantum mechanical model. So one of the first guys who contributed to this is Heisenberg, and he came up with this claim that it's impossible to know an electron's exact location and its momentum at the same time, right? Heisenberg was beginning to understand that there's always this idea of uncertainty and probability in the world, whether it's particles or really anything. So the more you actually know about its location, the less you know about its mass and velocity or its momentum, right? And conversely, if you know a lot about how fast it's traveling and its momentum, you're going to know less about where its exact location is. So it's almost like a spectrum, a pendulum going between these two. And it all has to do with observations, right? So one of his famous experiments is how electrons will behave when they're being observed versus, right, not being observed, and what you're observing. So if you're at all interested in this quantum mechanical model, Heisenberg is a really important character in this page of physics history, and his ideas are really essential to this being created, right? This idea of Heisenberg's uncertainty principle. And you can find some awesome YouTube videos on that will explain it to your heart's content. So, right, the more we know about its location, the less we know about its momentum, vice versa. So rather than placing electrons in these definitive orbits, right, just like Rutherford and Bohr, we had these exact, precise orbits where it had to exist. Instead, scientists are forced to consider the location instead of being a precise spot or orbit as a probability function, right? And this idea of probability functions is really important to this quantum mechanical model. Okay, so let's break down this idea of a probability function a bit more. So what Rutherford and Bohr called an orbital is really an area of high probability, right? So that's where you are going to be most likely to find the electron, right? Because the electron has a range of places it can exist. Maybe there's a 1 in a million chance that you'll find the electron way out here, but more like a 1 in, I don't know, 1 in 2 chance that you'll find it within this high probability or very dense orbital, right? So this is getting into an idea of a cloud electron model, right? And the electrons orbiting and being able to change their orbits slightly, but the highest probability location is what Bohr and Rutherford thought of as their quantized or their discrete orbits. All right, and this is just a nice little model of our most simple hydrogen atom with its ground state. So this is where an electron that's unexcited will be orbiting around this proton of the hydrogen atom. And right, it could exist in any of these low probability areas, but there's just a far better chance that it is within this this range of radii from our proton. So that's where we're most likely to find the electron, but it's not always going to be there, like Bohr and Rutherford thought, right? It could be, electrons can be somewhere else, but we will never know the actual location, so we can't describe its discrete path anymore, right? We don't know where it is, so we can't describe its path. We can only describe it as a probability function, right? Where we have a 95% certainty that the electron will be here, but there's a smaller chance that it's closer or further away. So just thinking about probabilities, right? We're not talking about sporting events or natural disasters. We're talking about these predictions, right? Exact predictions. So they are able to be calculated. You're not able to calculate an exact prediction of a sporting team, or any sporting event, but you are able to make an exact prediction on dice, right, or playing cards, right? The larger your sample size is, the more tests of rolling a dice you have, the closer you'll be to these exact predictions, right? So the same thing goes for the probability of an electron's location. If we kind of determine or estimate the position of an electron 10 times, we might find that maybe 8 out of those 10 times it's within our high density band, but 2 out of the 10 it's actually outside of that. But if we expand our sample size and do this, let's say 1,000,000 times, we'll be closer to that exact prediction, right? We'll probably have a better guess. So that's just an important note, that these probabilities are probabilities that can be calculated precisely. They're exact predictions, right? So something that has a set probability, not something that relies on estimates, right? Or best guesses, right? We're actually able to mathematically calculate this probability. All right, the quantum mechanical model of the atom has been incredibly successful, as I started off by saying. So we're far better off with this model than any of our other models. The basic structure has not changed since 1930. So even though everything around us is changing at a rapid pace, our understanding of an atom has been virtually the same. The basic structure hasn't changed. We've added little bits to it, and there is room for it to be improved, but that is far outside of the scope of this course. We're barely scratching the surface of this model and this understanding, so going on to anything further like string theory would be a little bit too much. So the best part about this is its mathematical description, right? The probability functions and being able to ascertain right, the shape and the probability of an electron being within these regions allows us to really look at chemistry in a new way. So that's not to say it won't be replaced. Most likely it will be, but as for now, this is an awesome mathematical description of atoms. All right, so we can now kind of use this model to correct all of the problems or explain all the problems that Bohr had. So this quantum mechanical model, right, helped out Bohr's model. It got rid of all of these unknowns. So the spectra for more complex atoms, right, when we have more than one electron, we're now able to use this model, where before Bohr's model could only be applied to single electrons. Right now we're working with different probability functions, different shapes and clouds when we're adding in more electrons, but this model has room for that because we have electrons acting like waves and their exact positions can't be known. The next point, why only certain orbits were allowed, right? Orbits were quantized. This is actually because the electrons form standing waves in these orbits, which is pretty neat, pretty amazing stuff. So it's kind of like the electrons are in their natural frequency, they're resonating, right? This is where we create a nice standing wave around our proton. This is going to be a hard drawing, but we have a resonant standing wave around the proton, right? Where a standing wave is just our classic transverse wave in this case, right? With our peaks and our troughs and our full wavelength, right? And as you go outside of that quantized or high density probability area, right, we're going to have more interference with out of phase electron waves. Third point, why the orbiting electrons did not emit electromagnetic radiation. This is because we're now thinking of electrons like waves, right? They behave like waves. They're not accelerating charges anymore. They're waves traveling around this proton. They will no longer be required to emit electromagnetic radiation, which is really handy because they don't, and they don't collapse in on themselves, right? So this all comes down to electrons, which we've thought of as particles, behaving like waves. And Bohr's final complaint or uncertainty point of uncertainty was why some spectral lines were brighter than others. This is because certain transitions have a higher probability of happening. So if there's a better chance of our hydrogen's electron traveling from its n equals 4 to its n equals 2, we're going to have a higher probability of emitting that, I think that was the green photon, right? So certain transitions are more likely to happen, and this is all based on the probability functions, where these electrons are most likely to be found, right? So higher probability means more often we'll be emitting those photons or absorbing those photons, depending on what type of spectral lines you're looking at, right? So some spectral lines will be brighter or darker than others, all based on this probability function. All right, that was very brief introduction to the quantum mechanical model. You'll have the rest of your lives to dig deeper into that. But for the sake of our course, that's all I got for you. So let me know if you have questions. Feel free to do some further investigation on your own because this is a really cool idea. All right. Good luck, everybody. Stay safe. See ya.